Hi everyone, this is Dr. Aeronautics. This is the eighth and final episode for our General Order Space Mission number 1 to Saturn. As you recall, we had returned successfully from orbit, landed safely on the runway, and then rolled a little bit off into the grass. We had a long landing, but we're back safely on the Earth without using any fuel on the way down, which I'm really happy about, and we're ready to perform an outbrief and put a bow on the mission. So the outbrief basically goes into three phases. The first phase is the collection of the mass collection of data. I'm going to collect quick saves from orbiter on the flight. I'm going to collect the flight data logs that we might have. I'm going to collect any screenshots that were taken. And I'm going to actually not collect all the videos. So what I'm going to do is I'm going to show you guys where to get the quick saves from, where to get the flight data logs from, but the screenshots and the videos really depends on what you use as your recording software or your print screen thing. So I'm not going to show those sections. And then phase 2 is to generate a report and respond to any actionable items. You remember there's that one area where all of the actionable items are stored underneath the fuel tabulation table. We're also going to put together a fuel performance graph, which basically shows this is the one time where we include the amount we've planned and the amount that we could have used together with the fuel that we did use. So all three are going to come together now, and we're going to get a snapshot of exactly how the mission progressed. The final element is basically zipping everything up. So that's updating the template. I'm going to show that. And then lastly, we're going to organize and collect all the data down to a single folder, and I'm going to place that folder in storage and publish the video. I'm not showing that last part because that's just simply everything that I've been doing thus far, and it's really up to you how you want to store the zip of the flight yourself. So we'll go ahead and get started now. Okay, so at this point, we have collected all of the images and quick saves. There's no data log, unfortunately. The videos have already been collected, and I can't really finish that until I finish this video. So we're good to move on to the next stage. So we're going to create a fuel performance chart based on this one. But when I do that, it's going to require that I edit the file as it is now, the report, the maneuver schedule with all of the mass values. So before I start manipulating it, I just wanted to take a snapshot again and export another file. So this is I had a launch export at the beginning, remember? This is a shutdown export at the end to basically guarantee that we have a example of what was in the report when we landed. Okay, so now to do this, we need three values. We need the actual rate, the red line, and the red line plus our reserves. So the first one started at 5120.83. So that's the fuel left in the tank, and it ends at 59.6. Okay, so it's column F. Column F is going to be the actual rate. The red line is going to be column L. And now I need to make a third column that is based on the red line plus the amount of fuel that we had on board. So we're going to create a new tab, and we're going to name this fuel performance at completion of mission. We can't do that. So just fuel performance at completion. So now what we need to do is pull this F column. So let's do, in column A, we'll say actual used. Column B, we'll make red line. In column C, planned usage. So now I'm going to do equals on A, and I'm going to pull in this number from the previous, and we're going to try and drag this down and see if it works. It does. Okay, so we're going to drag it down all the way to the end. And that is the end of the mission right there. So now I'm going to do the same thing over here on the red line. I'm going to go to mission information table, and I'm going to pull this value here, and I'm going to drag that down. Now the third number I need is based on the amount of reserves we had at the beginning of the mission. So that is going to be this value minus the difference between these two, which would be something like 200. Okay, so oh no, it's just this one at the beginning. And I think we actually want to add this. Let's try that. Okay, that looks good. So now what we do is we're going to highlight columns. Actually, let's see. We're going to select this data and see where it's getting its X names from. Okay, that it's getting the names from the maneuvers. So what that means is we need to add another column. We'll insert it A. And I haven't done this before, so this is kind of like a first time thing. Maneuver name. And let's expand these columns. And real simple, we just go here, pull that name, and we drag down. Let's remove that. All right, and then for these empty zeros ones, so that's Enceladus orbit insertion, I believe. Let's expand again. This is going to be Enceladus orbit, and then on Enceladus, and then Titan orbit, and then on Titan, and then Iapetus orbit, and then on Iapetus. And Then we need an Iapetus orbit again. And then there's one more Earth orbit, and then D orbit. Okay, so now what we're going to do is we can make those guys bold. We're going to highlight column A, hold control, and then highlight B, C, D, insert new chart, and I want this scatter plot here. Red is red, green is planned usage, and the actual usage is blue. I'm good with that. Okay, so let's move this down so that we can expand the chart as much as we can to show as much detail as possible. So the data ends there. We'll name this chart title Mission Fuel Performance Final. Okay, and now we'll drag down to this point here, and I will expand this as, I will expand this as wide as we possibly can on a single screen. So that's out to column P, row 71. Column P, row 71. Okay. And this is what we have. So you can see we had a little bit of problems initially on, it looks like the Earth ascent, maybe. And then everything is fine. And then when we actually eject, we actually end up catching up. And then we basically maintain the blue line, and then everything goes south here at maneuver number 30. So that's the Iapetus transfer injection, the Titan plane change, and the mid-course correction maneuvers to Iapetus. So this right here is where we had most of the issues. And then once we got really close to the red line, we basically held the red line or slightly above it the rest of the way down. So that's actually pretty cool. That tells you how accurate our mission planning here was. So we managed to fly this narrow corridor for the entire mission. So that shows you how accurate these sorts of calculations can be if you actually fly them. So I think I calculated a total moving average. Well, actually, let me go ahead and get those actual values. So row number 30. So that's the Iapetus transfer injection, and by the time we hit the Iapetus orbit insertion, we're fine. So the Iapetus transfer injection through the orbit insertion. So this right here is where we lost most of our edge. So if we take a look at the actual used here, and then go back to Iapetus transfer injection to orbit insertion, Iapetus transfer injection to orbit insertion. So this first burn, the second burn, the third burn, the fourth burn, all of these burns were a complete disaster. So as you recall, when we took off from Titan, I think I tried to force a bad transfer because I didn't want to wait. Orbit not fully circular due to atmospheric effects, so there was that too. The other thing too was the Titan ascent. So let's try to decompose and figure out what went wrong here. So on the Titan ascent, the problem with the Titan ascent was incorrect mathematical estimate for, and I'm going to note this in the report, incorrect mathematical estimate for ascent on Titan. The second part, the transfer injection, uh, the pseudo root cause was forcing a bad timing. The true root cause would be the reason why we were off in the first place, which was incorrect method for determining difference. I should say home and transfer window. And that's going to be an action. And that action is going to be create a checklist for home and timing, so that I don't try to remember it again and remember the wrong way. Because it had been like 3 months since I had done Orbiter at all, and so I got really rusty here. That's a fact. And I kind of felt incompetent as well when that was going on. Let's see if there's any other things we want to pick out of here. Not worried about the good stuff. More worried about the bad stuff. Oh, actually, I was wrong about this. So the blue is the actual used. So the blue is how much we did use. The green is how much we were supposed to use, and the red was how much we could use. There we go. So we were actually above it for certain period of time, which means this now is of interest. So that's the Enceladus ring avoidance. So here's another reason. Did not properly determine ring avoidance planning. And I think the root cause for that was difference between orbiter and real life. And that's kind of unfortunate because I rely on real life astronomy in order to determine what the situation is. And if real life astronomy differs from the orbiter simulation, we're going to have issues. And we kind of have to cheat by going there to know that. So maybe that's just sort of science that we brought back, like in Kerbal, we're doing science. We did science at Saturn and found out that no, in fact, there are a few differences between the Saturn system in real life to the Saturn system in orbiter. And if we were doing a science mission, that would be our conclusions, is that there are significant differences between the atmosphere of Saturn and atmosphere of Titan in real life, and as how they were simulated in orbiter. Let's see, then we get good, and then we get a margin, and that margin slowly evaporates, and then it gets really bad right here. So what is this? That's the Titan ascent. Okay. So we're okay again. We get really bad, and then everything is okay from here on out. All right, so we've got three problems. We've got the problem of the incorrect mathematical estimate for ascent on Titan. No action there. I guess the key takeaway is reference the value for future missions. And there's no action there because remember, that's already part of the planning phase of mission planning. Remember I said let's go back and examine the previous flight for any actions that came out of it. So this will be one note, and we have it right here under actionable items in flight. So we're okay. So I've got that down. Then there's the bad timing. We have the action to create a checklist from that. And then the third, did not determine the ring planning. That's the same thing with the Titan Ascent. That's reference the old information from the previous flight in determining information to use on the new flight. So that completes our mission fuel performance chart. I will go ahead and save this, and we're good to go to the next item. Okay, so the next thing to do is to respond to the actionable items. So we have to search for them. So I'm going to come out here, and we have the notes area. That is one location that they're going to come from. Then we've got the scratch zone. We'll check that second for anything that might be hiding in there. And then third, whatever ends up in the actionable items list, we're going to record it. So starting up here, that's a note for me. Let's see, this is another note. Then we've got a suggestion, another suggestion, and this one definitely came from the previous flight, so we can leave that. These are notes. More notes. It's a note. These two are notes. Alright, this one's a little bit interesting. Orbit not fully circular due to atmospheric effects at 2905. Okay. Alright, so that's going to be an action. Then we'll do return to Saturn. Actually, that's Titan. Return to Titan. Atmosphere differs from real life. Well, I guess that's not an action. That's just an advisory. All right, we're going to add that one here. So we're going to put that in actions here. We'll just say note the Titan atmosphere differs from real life. Okay. Now let's see. We were in column U. That one. Okay. And then the rest of these, that's a note. That's another note. All right. So now we're into the scratch. Actually, no, it's the trip notes and then the scratch zone. So there's 4 locations that we need to address. This is just information. More information. More information. Okay, now we're into the scratch zone. So this is just information here. Okay. That is already addressed. That's the difference in the gas giant altitude. If I had been at 1,400 kilometers, we wouldn't have dipped into the atmosphere as much as I was concerned. So that was kind of an issue. I guess watching things. Maybe that's an action. Let's see. Check. Maybe I should put recheck. Periapsis for atmospheric passes many times. Okay. All right, where was I? When I was in the scratch zone, it was right there. Okay, so then I've got my calculations here. So then we release the probe. Okay, I didn't see any additional actions. They ideally should be all in this area here. And then I had written down one action here, and that was create a checklist for human timing. Actually, I might be able to add on to that. Try adding onto checklist for determine takeoff time. So actually defining that. All right. Okay, so now we've got all of our actions, so we need to figure out what to do with them. So there's going to be update a checklist or other product. Then there's notice for next time. And then there's the third, which is solve discrepancy. And that one really stinks because that's basically we have to think hard about it. You know, it's not just a process. So let's see, the math on the probe release, that's our first solve discrepancy. Then we've got inclination readouts on transects and aligned planes or ecliptic. I thought that was in our notes here. Okay, I guess it does not. All right. Well, then in that case, we're going to put that into notice for next time. All right, then let's see. UMMU, remember they have O2 durations. That's definitely a notice for next time, just, you know, in the planning phases. UMMU, I got that. If you do a probe, you need to separate the arrivals so entry doesn't happen during a critical burn. It's too much at once. That's definitely a notice for next time. All right, now I've got more. I need to make more room here. All right, we'll just drag and drop from here on out. So what happened on the Enceladus ascent to cause an 87-degree inclination after following a 38-degree takeoff heading? Okay, that's another one of those solved discrepancies. That's another thing that's a mystery that we need to solve. At 600 kilometers, Titan's atmosphere was significant. Why did you not realize this would happen? Okay, that's another solved discrepancy. Notice that 330 kilometers is, however, a great altitude to perform an aero capture without atmospheric entry occurring. Notice for next time. Okay, the Titan landing maneuver cost 3 times more than expected. Why? That's another solved discrepancy. The math for determining the launch time for Titan to Iapetus was mirrored across 90 degrees. That is probably an update of product. Because we basically need to, adjust what time you launch. Okay, Titan ascent was like 3 kilometers more. That's a notice for next time. Note that Titan's atmosphere is simulated below 700 kilometers. I think I put that on there in case I didn't notice this one. So this one is basically a doppelganger of this line on 157. So they're effectively the same action. I'll delete that one. Plan the Iapetus ejection burn better, because after the burn you will swing 45 degrees outward. That's a product update. Need to add a boost burn to leave Iapetus. Boost burn to leave Iapetus. I don't remember what that was. Yeah, that's undecided. Okay, so I'm gonna move this up, and I'm gonna have to refer to my videos for that because I do not remember that. Export your orbiter re-entry calculators as PDFs. They were perfect. I did. I did. Okay, so I didn't save this as a PDF, but I did save it nonetheless in my master flights folder. So this is titled Orbiter Example of a Perfect XR2 Reentry Solution. Remember, we were deeming it perfect because we had managed to land on the runway. It was a little bit long, but that's not part of the reentry. That's part of the glide slope. You know, that's something that we can easily fix. Without using any fuel or drag brakes. And we opened the gear right around when we were supposed to open the gear. So really the only thing we need is a sort of like drift down, and I think that was a separate action. So I can right away close the action of this perfect XR2, saving that off. All right, so let's add a fourth section here that just says closed. And we'll drop this down here. I already took care of that. All right, note the Titan atmosphere differs from real life. Okay, so this is, I had already noted this in the first hand. So at 600 kilometers, Titan's atmosphere was different. That's kind of asking a little bit question. It was significant versus different. They're not really the same question, so we got to have this one too. Solve that discrepancy. Then we have recheck periapsis for altitude or for atmospheric passes many times. That sounds like a product update. Maybe we need a new checklist. Okay, and then last one, create a checklist for home and timing. That's definitely update a product. Okay. All right, now I got to figure out what this boost burn thing is. Okay, I remember this. So this boost burn thing was related to our periapsis not being where the periapsis in the orbit was. So I think that is a plan for next time. And let's clean up this language a little bit. So let's see. Notice for next time, if returning from an outer moon, mind its orbital timing with the ejection date. The moon may not be in the right place to eject. Okay. All right, so let's order these based on increasing difficulty. So if it's closed, we don't need to do anything about it. The next thing is um, notice for next time. That's going to stay there. So it's just a notice. Then we have, I think, update a product next. Yeah, and then the worst of them all is solve discrepancy. All right, so let's talk about these updating a product. So the math for determining the launch time for Titan to Iapetus was mirrored across 90 degrees. All right, what needs to be updated here? So this is launch timing for going from one to another. So I took off late and didn't realize it. So I need to update the calculate takeoff time. Checklist. Then we have plan the Iapetus ejection burn better because after the burn you will swing 45 degrees outward. Actually, that's a notice for next time. I don't think I understood that exactly right. So that's when leaving the final moon. That's not an update product, so that's nice. All right, recheck periapsis for altitude passes many times. All right, so we need a atmospheric approach checklist. That's going to be a new one. And then lastly, we have create a checklist for home-in timing. Suggest adding onto the checklist for determined takeoff time. Okay. So calculate takeoff time to the checklist. Wait, is this the same thing? The math for determining the launch time for Titan to Iapetus. And this was created because the launch timing was wrong. So these are the same thing. So there's only two updates that need to happen. And then we get into the discrepancies, which are their own beast. So, all right, I'm going to update the products now, and then once they're updated, I'll show you guys what I did. Okay, here we go. So ground cockpit startup determine launch time using TransX. That's all I had to say. Just don't try it any other way. Just try it using TransX. Second, we have a new checklist. It is called Atmospheric Approach. And very important, the most important line in here is cross-check perigee altitude every halving of time from periapsis. So that allows us to avoid a situation where we get periapsis that's drifting too low. And that is it. This closes recheck periapsis for altitude passes many times and create a checklist for home-in timing. So we can move these guys to closed and delete this section to update a product. It doesn't exist anymore. So then we've got the same notice for next time. And now we're on to solving discrepancies. So Your math on the probe release maneuver was fundamentally wrong. So I thought this would be as simple as changing the velocity from one direction to another. But I think the issue is that I am not looking from the perspective of v at infinity. So we're getting a penalty by the Oberth effect. So let me take a look at my Hohmann calculations to see if I can get any possible reasons for that. And before I check, the anticipated value for the inclination, or no, it was the probe release maneuver. Thought 52.5, actual 257.5. All right, guys. So interesting conclusion here. So I said that the math was wrong, but it wasn't. It was actually right based on what I checked. What happened was my orbit collapsed, and I did not pay attention to that. I was so obsessed with it was the exact same thing that happened when we were approaching Earth, where I was like obsessed with approaching the core of the Earth, and then realized too late, oh wait, we don't want to go into the core, we want slightly into the atmosphere. And we had to burn the engines for a long time to do that. So this discrepancy has now become, when approaching a planet, be mindful of what the target actually is. Atmosphere, not core. Okay. Now I need to figure out whether that's a notice for next time or a product update. There's no checklist for approaching. And if this is somewhere that would go in a checklist, I can move that one up. So that's a notice for next time. Nice. Okay, moving along. What happened on the Enceladus ascent to cause an 87-degree inclination after following a 38-degree takeoff heading? Yeah, that's an interesting one. I'm going to have to watch that. Okay, so the next mystery was solved. What happened? So what happened was when I saw 87, I just assumed it was equatorial, and it wasn't. It was ecliptic. And remember, Saturn is inclined like 29 degrees or 27 degrees to the ecliptic. So what I was reading off was a number that didn't really have any significant relevance. The actual inclination was about 66, which is consistent with our high latitude. That actual number being the equator version. And I said I wanted, I think it was 47 south? Yeah, 47 south, and took off fairly north-south, so that's going to add to my inclination. So the minimum inclination if I took off at 90 degrees would have been 48 degrees. So that explains that one. We can now move it to the closed area, and I don't need these things anymore. Alright, so moving that one up. Now we've got 3 discrepancies left. 2 of the 3 have to do with the Titan atmosphere. So, alright, how did I come up with the altitude to use for Titan? That might actually be a pre-planning phase determined. Let's see, we had this one here. All right, yeah. Let me look into. I'm gonna actually have to go to the mission planning episode to figure that one out. Okay, guys. So we know. Note the Titan atmosphere differs from real life. That differing was why the atmosphere was significant. The problem is, again, Orbiter defines the atmosphere as being 288 Kelvin, not 95 Kelvin. So what that does is that expands the scale height by a factor of 3. So we were seeing the pressure that we should have seen at 200 kilometers up at 600. And that is not what should be happening. So the scale height is inflated. That's a notice for next time. And I think I remember this being the case for Saturn. Or no, Saturn was correct. Never mind. Okay, so now we've got one discrepancy left. The Titan landing maneuver cost 3 times more than expected. Why? That one should be a little bit easier. Alright guys, we have solved all mysteries regarding the action items. So why did it cost 3 times more than expected? Because the atmosphere was off, causing a higher orbit that we needed to reduce our altitude from. Simply put, we weren't in 200 kilometer orbit like we were, it was really 600. So this is all pointing to several root causes. So this item is due to differences in orbiter atmospheric sim versus real life. The other key thing, let's see, that was my error, and it really didn't matter anyway. I was just like, why is it 87? And I didn't know. Let's see, create a checklist. Yeah, we did that. Let's see. Then we had changed these, right? So that's again differing in real life. And then that's our other root cause for several things. Target the altitude on a planet, not the core. Okay. All right, so we have several root causes that I can write up in the final report. It's going to be really short. I'm going to clean up the remaining items here so that they're a little bit more understandable in the future. Okay, here we go. These are the final actions as they stand in the report, or the mission information table, and we are now ready to update the template for future flights. Okay, I have saved a new template for Orbiter Generic Flight 032622. Next time I fly a mission, this is what we're going to use. So, let's go ahead and look through here. These are examples, so we're going to leave them. Scroll down. Now we've got, let's see, fuel amounts here. Then we've got flight notes examples. I'll leave those. The scratch zone, there's nothing to add there. Okay, so we just add actionable items from previous flight. Okay, so I've just pasted these in, and some of these are going to be repeats, so we have to go through and look for those. So, Earth circularization burn deserves its own line. Transacts ELS adjustments. How to perform the inclination adjustment burn. I thought that I had a note here on inclination readouts on transects reading the ecliptic, but it doesn't look like it right now. The UMMU will leave. The probe, that's new. And then the Titan one is new. For this, I'm going to say refer to the Saturn flight of 009262021. I think that was the one. If returning from an outer moon, yeah, that's new. So really all of these are kind of new. Let me see if I can get rid of any of these older ones, because there's a lot here. So circularization burn deserves its own line. We know about that. To know when to burn for transects inclination adjustments. I don't want to remove that either. To perform the arrival inclination burn. That's important too. That's something that I could easily forget. Landing economy. I don't want to remove that one either. 18-degree plane change thanks to ejection orientation course. Do I have a note about that? Let's change this to use ejection orientation course to reduce plane changes before home-in transfers. Okay. The constant perturbation present. Yeah, I don't want to get rid of that either. I don't want to get rid of that one. A final plane change should exist to precisely align the re-entry path. Yeah, I mentioned that one too. This one I don't want to get rid of. That one I don't want to get rid of. Read the previous flight's MIT for more notes so you know. Yep, do that one. Inclination adjustments are in ecliptic. So let's get rid of the specific ones. So let's see, UMMU. Let's see the probe. Okay, that's one that I can knock out. Because of that. If performing a Titan ascent, that's another one that I can knock out. If returning from an outer moon, I need to leave that one. When ejecting from a moon, definitely leave that one. When approaching a planet, be mindful of the target. I'm definitely not erasing that one. And note that the Titan atmosphere differs from real life. That's important because it's basically every planet that's not Earth. So just heads up. In fact, yeah, I'm going to secularize this. Notice the atmospheres differ from real life. Remember, orbiter defines the atmosphere of 288 Kelvin, not actual Kelvin. All right, I think we're done. So that saves the generic flight update. So that's our new template that we're going to use next time we fly. Okay, so here's our final report. We're going to do a Word document, and it should be pretty easy. It's going to be super simple, shorter than a lab report would be even. So what we're going to do is we're going to say mission objectives. Take off from Wallops Flight Facility on Earth. Fly through the Saturnian atmosphere. Drop a probe into Saturn's atmosphere. Fly between the rings. Land on Enceladus, land on Titan, land on Iapetus, return safely to Wallops Flight Facility on Earth. Mission status. All objectives were accomplished. So let's talk about it. So we went through, okay, we took off, that was fine. Then we flew through the Saturnian atmosphere. The atmosphere of Saturn was flown through very deep because we did not pay attention to periapsis drift downward. No damage resulted. The probe dropped into the atmosphere during the burn, causing us to become heavily distracted. And data logging was not performed because of this. Also, it was dark, so wasn't particularly useful. We missed a lot of sightseeing there. Let's see. Then we landed on Titan, and let's see. Titan was landed on successfully, but fuel calculations were inaccurate due to the differences in orbiter from real life. And then let's see, lastly, in the case of Saturn, Earth, and Titan, more fuel than necessary was expended in approach ink adjustments because the core, not the desired orbit, was targeted for too long. Okay, so I'm going to do fuel use history now, and what we're going to do is we're going to import the picture from the report. Okay, so there's our final mission fuel performance, and here's our final fuel numbers at end of mission. 5,120.8 kilograms of fuel expected / planned to be used. 5,313.3 kilograms actually used. Difference between planned and actual, 194.5 kilograms more than planned fuel was used. Percentage more than total fuel actually used, 3.8%. Total fuel calculation accuracy, 96.2%. That's the grade that I would give us on this mission out of 100. I think we got an A, fairly solid A, but I wouldn't give us an A+. Fuel reserves at the start of the mission, 245.8 kilograms. Total fuel reserves at the end, 51.3 kilograms. This is the next episode. There's no more analysis more than what we're doing now. So then I need a synopsis statement here. We landed with enough margins in the tank. Still more existed because nowhere near the allocated RCS fuel was utilized. However, approximately, and I need to do this math here, so we used 51.3 over 245.8. Approximately 79.1% of the reserves were used, meaning that further what's the word I'm looking for? Further decreases in margin percentages should not be undertaken. So basically what I'm saying here is we used almost all of our margins, so don't try to cut the margins even smaller than what we planned for, because this is about the kind of performance that we can do with based on what we're getting. Final statement. Several action items were identified in the course of this mission. They should be heeded in future missions. And let's get them. So here's our closed items. And then we need our notice for next time items here. Signed, Dr. Aeronautics. And I'm going to save this in the same location as before. Okay, folks, this is it. This is our final mission and everything in it. We've got our screenshots, our quick saves, the video is about to come together. I don't zip because I have plenty of hard disk space, but this is where we leave the mission. This one is done, and we're ready to begin the cycle again of planning a new mission from the very beginning. I hope you guys have seriously enjoyed this, and I've showed you how a lot of hard work can result in a lot of amazing demonstrations, and basically making how far can you make your rocket fuel go, and how far can you make your oxygen and planning go. What are your capabilities? What can you definitely not do? We definitely took advantage of everything that I could really think of, with a little bit of room for improvement. So thank you guys for joining me. Coming up, we're going to roll the screenshots, every screenshot that was taken during the mission. This should be quite a long segment. So grab some popcorn, sit back and relax. And thank you guys for joining me. I will see you guys next time. Bye bye.